In this section, we'll be talking about the behavior and characteristics of the graphs of rational functions. But before we do that, we want to establish what we mean by a rational function. Rational functions are functions of the form p of x over q of x, where p and q both represent polynomial functions. So we have the quotient of two polynomial functions. That's what dictates a rational function. Now that we're dividing by something versus polynomials, there was no division, just multiplication and addition or subtraction. We have to be careful because we can't divide by 0. So what that means is any values for x where we have our denominator, q of x, equal to 0, implies a restricted value, a value that's not included as part of the domain of that function. One of the simplest rational functions that we can look at is called the reciprocal function. F of x equals 1 over x. The graph on the left is a graph of this function, f of x. And we can tell by looking at that expression, 1 over x, that this function will be undefined at x equals 0, or has a restricted value that tells us x cannot be equal to 0. The fact that x is outside the domain of the function is what creates this sort of natural barrier, this invisible straight line, vertical line, that our graph curves towards but never crosses. We refer to that as a vertical asymptote. So our function, f of x equals 1 over x, is undefined at x equals 0, and that's why we see that vertical asymptote occurring, which is again a vertical line that our function will approach but never cross over. The graph that we have on the right looks identical to the graph of f of x, but this is actually the graph of a different function, which we'll call g of x, is equal to x minus 2 over x times x minus 2. We can see from setting the denominator of this function equal to 0 that x cannot equal 0 or positive 2. At x equals 0, we see the same behavior that we had with that graph on the left. We have a vertical asymptote at x equals 0, but what we don't see clearly in this picture is what's happening at that other restricted value of x equals 2. And we have to be careful with this because lots of times graphing tools like graphing calculators, other online software, won't show us this other restricted value. So we need to know or somehow indicate that what we have is an open circle in the graph when x is equal to 2. So different than the vertical asymptote, which is a line that our function is approaching and sort of curving towards, this hole in the graph is just a single point that we refer to as a removable discontinuity. Since that x value is outside the domain of the function, the curve just skips over that point, but otherwise kind of appears to just keep going. So we have our function g of x, which is undefined at x equals 0 and x equals 2. In our next section, we'll talk about how we distinguish when we have an asymptote or a removable discontinuity. For now, we just need to be aware that those are two different types of behaviors that can occur when our function is undefined for a specific value of x. Next, we want to consider what's happening to these two functions as they approach their vertical asymptote. What we can do is trace along our curve as it approaches x equals 0 from the left. We can see that what's happening is our curve is just continuing to go down and down and down into lower function values. And if we trace along our curve and approach that asymptote from the right, our function is heading up and up and up, headed to larger function values. So this means that as x approaches 0 from the right, our function, or both functions really, approach negative infinity. I'm sorry, that should be positive infinity. As we approach from the right, we're approaching positive infinity, and as x approaches 0 from the left, our functions approach negative infinity. So what we're saying is, as we approach that asymptote from the two different sides, we can see that our function values are headed, in this case, in opposite directions. And that's what we're indicating here. We refer to this discussion as the local behavior, or identifying the local behavior of a function. What direction is the curve heading as it approaches that asymptote? And we're going to introduce some notation that we can use to summarize those two bullet points above. We'll say that as x approaches 0 from the right, we'll use this little plus sign that we write sort of like an exponent for the 0 to indicate that we're approaching 0 from the right. Our function f of x is approaching positive infinity. And then similarly, we'll write that as x approaches 0 from the left, where we're writing a minus sign, sort of like an exponent attached to that 0, that's indicating that we're approaching that value from the left-hand side. Then our function value f of x is approaching negative infinity.